Thank you very much for joining us on this webinar on developing homegrown rehabilitation robotics expertise in developing countries using Nigeria as a case study. Over the next 1 hour or so, I hope to set the stage by identifying the problem, after which we take a look at a few emerging alternative therapies that can be used in solving this problem. And then we make a case for robot-assisted therapy as a key component of what a successful approach to solving this problem might be. After which we'll take a look at some issues to be considered by LMICs as they try to adopt robot-assisted therapies. We'll do this looking from the vantage point of some work currently being done by the Ile-Ife Rehab Robotics Research Group. And finally, we'll quickly take a look at some of this work that we've done over the last 1 or 2 years. So the source of the problem, in a nutshell, it stems from the trends we notice with regards to stroke globally. LMICs account for just 62% of countries globally, and yet have 86% of stroke deaths and 87% of disability adjusted life years from stroke. And perhaps most alarmingly, over the last 40 years, we've seen an increase of over 100% in stroke incidence in LMICs, while in the same period, stroke incidence has actually declined by 42% in high-income countries. Well, if there's a silver lining at all, it's the fact that our understanding of the disease is now that with proper physiotherapy, most of the motor, cognitive, and functional impairments after stroke can be reversed. The bad news, however, is that LMICs are generally handicapped in this regard for some of the following reasons. In particular, I'd like to talk about the problem of low numbers of clinicians in LMICs. I'm taking Nigeria as a case study, as at 2020 we had 4,587 physiotherapists, 200 neurologists, and 137 occupational therapists, all to handle a population of 206 million. Clearly, there's no way for this minuscule number of clinicians to handle this large number of this large population, or the large number of stroke survivors threatened by the trends we have observed. And you can therefore see why some people believe that LMICs like Nigeria have to urgently consider alternative therapies. Well, as it turns out, there are quite a number of these alternative therapies. The ones on the right are relatively low-tech, body weight supported treadmill training, constraint-induced movement therapy, task-oriented therapy, community-based rehabilitation, home-based rehabilitation. These have emerged over the last few years, but are now increasingly considered as conventional methods or extensions of conventional methods. More intriguingly, however, we have a class on the left that represent more high-tech alternative stroke rehab therapies. Robot-assisted therapy is an innovative form of rehabilitation and that enables highly repetitive, intensive, adaptive, and quantifiable physical training using robots, where the robots replace to a large extent the forces or torques or constraints normally supplied by a human physiotherapist. In transcranial DC stimulation, it's a non-invasive brain stimulation technique in which we use constant DC currents of milliamp range delivered to the scalp of stroke survivors using electrodes. This current is applied for up to a few minutes to a few tens of minutes at a time. Transcranial magnetic stimulation uses changing magnetic fields which induce currents to flow through specific targeted brain regions, while virtual reality systems are systems in which computers simulation is used along with an immersive graphical projection system as the primary outputs, which allows users to interact with an artificial 3D environment. And in VR systems, you can actually use gloves with sensors to deliver haptic feedback. That means the users can actually have sensory feedback by touch using gloves fitted with sensors. Functional electrical stimulation systems are systems in which low amplitude electrical pulses are applied to muscles to induce movement when the energized muscle fibers contract or expand. And finally, brain-computer interfacing systems allow human interactions with machines by acquiring signals from the nervous system. In doing this, BCI bypasses some portion of the normal nervous system pathways in the process of communicating with the brain. So these are 6 different classes of high-tech alternatives that have been deployed for stroke rehabilitation over the last few years to varying levels of success. But of this, I will be focusing on robot-assisted therapy in this talk for some of the reasons which Professor Laogun has already highlighted. In our opinion, RATs hold special promise for LMICs. Unfortunately, not much attention has been given to these new therapies in LMICs. In a study conducted by our friends in Ibadan, Suka, they found out that less than 5% of randomized controlled trials involving RATs were conducted in LMICs. And you can see the picture is not much better for the other high-tech alternative therapies. The best of them is transcranial DC stimulation, of which 21% of studies were conducted in low and middle-income countries. We should of course bear in mind that this data would have been much worse but for the effect of countries like China, which even though they are considered LMICs, they do have resources that rival some high-income countries. So if you remove countries like China from the equation, there's almost nothing being done in LMICs on these new or emerging alternative therapies for stroke rehabilitation. As I previously mentioned, we will focus on robot-assisted therapy in this talk, and maybe a good idea to quickly talk about what's so special about robot-assisted therapies. Well, RAT is unique because it's the only high-tech option that provides a consistent way to work the muscles and reinforce the link between cortical brain, that's brain activity, and muscular activity, the way conventional therapy does. This is primarily because robots can generate torques or forces or provide support the way that is similar to how a normal human physiotherapist would. But not only this, robots also hold potential of becoming even better than trained physiotherapists. We can tag sensors to them and make them more perceptive than any human being. In fact, robots could one day become better than humans. Robots can train patients with intensity and for longer than any human physiotherapist can, without observing a drop in performance. But as of today, robots do have some question marks hanging over them. And if they are to be considered by resource-strapped LMICs, we have to face and discuss these limitations. First, their effectiveness is still in question. And this may sound surprising to many listeners who probably have heard one or two things about robots being used for rehabilitation. When we see their effectiveness is in question, it's not that they don't work. It's that when most of the large randomized control studies that have compared the effect of robots and conventional therapy have found improvements in both groups. That is, they found improvements in groups using robots, and they found improvements in groups using conventional therapy. But when they compared the two groups, there usually isn't much significant difference in the performance of the two groups. So what we can take from this is the fact that the results so far suggest that robot therapy can be as effective as conventional therapy, but not necessarily better. And in some cases, they found out outright that robot therapy can be worse than conventional therapy, although there are much fewer of the studies have suggested the latter outcome. Secondly, robots can be more expensive for the same amount of impact. Yes, we do have some studies like the Wagner one that found lower costs for robot-assisted therapy compared to conventional therapy. But generally speaking, for the same impact, most studies have found out that robot-assisted therapy may be a little more expensive. This is made more difficult by the fact that it's complicated. It's difficult to compare costs, because normally robot-assisted therapies will not perform the full spectrum of support that you have in conventional therapy. So often in the robot-assisted therapy studies, there will be some elements of human intervention, and so this makes comparison a little more difficult. But still, there's no running away from the fact that robots still tend to be more expensive for the same impact, in quote, than conventional therapy. Robots have enjoyed more success in surgical robots have enjoyed more success. They've been deployed far more than rehabilitation robots, and so they have a lot more data. And there are studies, for example, an interesting study by Gekis that how this quote I found interesting. They revealed that under specific conditions, robots have the potential to become cost effective. If you read between the lines, this suggests that right now, generally speaking, robots still tend to be more expensive. That's fine. Talking about the barriers to robot-assisted therapy, of course, they require more infrastructure, and they require more technical specialists, which is something that should not be underestimated in a resource-constrained LMIC. But having said all this, we can remain full-throated in our endorsement of robots for a number of reasons. For one, in every industry in which they have been introduced, robots have rapidly improved over time. And really, it's a matter of time before the effectiveness, in fact, the superiority of robots over conventional therapy is unequivocal. Taking an example from surgery robots again, the Da Vinci surgical system. So this image is from one of their literature that shows the supposed advantages of the Da Vinci system deployed, which has been developed over the course of just over 10 years. Right now, it has these advantages over conventional surgery for the types of surgery for which it is appropriate. So you can see already, compared to normal surgery, you have reduced length of hospital stay by patients. There are fewer complications arising from the surgeries. The patients need less blood transfusions. There are lower rates of infections. We have fewer hospital readmissions, and patients are able to return to normal activity. These are already advantages claimed for the Da Vinci surgical system when you compare them to highly trained human surgical experts. What this tells us is that over time, robots do get better, and there's evidence that they can't get better than trained human experts. There's no reason to believe this won't be true for rehabilitation robotics. Secondly, the cost of robots will drop. So this chart shows how the unit cost of robots have dropped over the last 25 years, and projects what will happen over the last 5 years or so. And you can see the price, the cost halves, reduces by 50% of every 5-6 or so years. Between 5 and 6-7 years, the cost reduces by half. And here, a chart from the International Federation of Robotics shows how robot costs, average prices have dropped relative to labor compensation, that's human labor compensation, in some developed countries over the last 25, this is last 30 years really, also. So robots will reduce, the cost will reduce, there's no doubt about that. So what's the case for robot assisted therapy in LMICs? It's actually very simple. The trend suggests worsening stroke statistics, and there is no reason to expect any significant improvement in clinical workforce or economic system in LMICs over the next few years. Now, a significant portion of cost of imported robots will be manpower costs, which tend to be much higher in high-income countries. So there's a case for LMICs to develop their own robots, as this will possibly reduce the costs. Even though we know manufacturing capability is limited, that should be more than offset by the reduced cost of the human labor in the overall cost. And yeah, and we do know, and this is a case we are making in this talk, that we can develop robotics expertise locally. If you factor that, if you add to that the fact that robots will definitely get cheaper and will definitely get better, then we have to really consider robot technology. Over the next few seconds, I have a clip that I just show. I find it's an interesting clip put out by Robotics, a company that makes robots for different special scenarios. I want to point out that the first robot made by this company was presented in 2004, I believe, and in less than 20 years, this is how far they've come. In this period, if to compare human performance in a 100-meter dash, for example, the improvement in the human performance in 100-meter dash has been less than 0.5 seconds. Yes, less than probably 0.4 seconds in the same time. So robots improve much faster than humans can, and what is more, their improvement often tends to be exponential. So if anybody is going to ask if you're going to bet against robots becoming better than human physios and cheaper than human physios, my suggestion would be don't bet against robots. Okay, so having said that, what will it take to get LMICs to get to the point where we use robot assisted therapies? Well, that depends largely on whether we want to just deploy them or actually deploy them, because there's a difference between the two scenarios. For example, many people think China is the global leader in robotics, and in a sense, yes, they are a leader, but the distinction is important. In implementation, China is one of the leaders, if not the leader, in implementation and deployment of robots. When you're talking about development of robots, not really. You still have countries like South Korea, Japan, United States, and even Germany ahead of China in the pecking order. So there are two different propositions that you want to develop or you want to implement robots. And so LMICs, probably individually, we have to decide which of the paths they want to take. And if, for example, you are taking the development path, then the level of innovation required is much steeper than if you're just looking at implementing or using robots. In both cases, we need to work on our curricula to ensure that the outcomes properly lead to new cadre of the workforce that can properly operate, maintain, use robots. But of course, in the development path, we also have to be capable of churning out engineers and clinicians who can develop new robots. So that's education, cross-disciplinary integration is important, innovation is important, And in terms of manufacturing, if we're developing robots, then of course the manufacturing expertise has to be there, which doesn't necessarily have to be there if we're just deploying them. And in both cases, policy is key. Policy is key because robot-assisted therapy is not something that LMICs will naturally gravitate towards because of our known problems. So the government has to stimulate interest in robot-assisted therapies in either path chosen. And we're going to assume that infrastructure can't be changed overnight in a country. So we know that robots will require things like better power supply, usually require support structures that may not be there. So we are going to have to take that as a given because we can't assume countries will change their infrastructural ecosystem in just a few years. So what has to happen is that LMICs will have to find innovative ways to work around the problems. For example, robots that have backup power systems and things like that. Okay, so let's take a quick look at a small research group in an LMIC working to create expertise on robot-assisted therapy. The Ife Robotics Research Group is a research group based in Ile-Ife. Ile-Ife is approximately 150 miles from Lagos, in the southwestern part of Nigeria. This is a photograph of OAU showing the College of Health Sciences, the Faculty of Pharmacy, Faculty of Dentistry, I believe, and parts of the Faculty of Technology, where most of the foundational members of the group come from. Some of our key members also come from the Department of Medical Rehabilitation in the nearby Obafemi Awolowo University Teaching Hospital Complex. While this is called the Ife Rehab Robotics Research Group, our scope is certainly widening. We now have partners, friends, and collaborators in Ibadan, which is less than 50 miles, approximately 50 miles from Ife. They also have a top-notch university and rehab program there. University of Maiduguri, collaborators in the USA, in Germany, and we're playing an active role in advocacy for development of RAT technology in LMICs. And in this, we have partners from Namibia, USA, Mexico, and Costa Rica. So, using the Ife Rehab Research Group as a case study, what are some of the thoughts about education in what are some of our thoughts about education in LMICs towards developing RAT expertise? Well, for starters, biomedical engineering is key. It's critical you have a biomedical engineering program, and in this regard, Nigeria still has quite some ways to go. We have 9 BSc programs in biomedical engineering, with only one of them accredited by the engineering body, by the body responsible for accrediting engineering programs in Nigeria. There is still some dissonance in the BME program as seen, conceptualized by this engineering body, engineering accreditation body, and the National Universities Commission, which is in charge of accrediting university programs. So we don't have a program in biomedical engineering accredited yet in the country at the graduate level. And in a nutshell, as I said, mature biomedical engineering programs are mandatory for sustainable development in robot-assisted therapies. So I think the take-home point from here might be that Nigeria has started on the path towards sustainable RAT technology therapies because we have a few biomedical engineering programs, and the number is going to increase over the next few years. Now, it's important to note that research and development in RAT requires close collaboration from experts in multiple disciplines, including robotics, mechanical engineering, electrical engineering, material science and engineering, neurology, physiology, computer science, and a lot more, mathematics, and so on. And so it's better to have institutions that have all these programs mounted locally if we are going to have sustainability, because there's this cross exchange of ideas that is required to have all these disciplines working together, and if some of these disciplines are not domiciled locally, it becomes more challenging. And one of the characteristics of LMICs is that logistical problems that look to be minor in HICs usually take on a more complicated and difficult aspects in LMICs because of our typical resource constraints. And it's important to once again mention that biomedical engineering is a natural melting pot for disciplines. And one of the reasons why this is important is that it allows the different disciplines to work together within the same confines, and allows a melding of perspectives, which is not given, because clinicians and engineers and engineering researchers actually have different perspectives. Your clinician wants to solve problems, they want to save patients now, while your science engineering researchers require time to go through proper engineering process of design, validation, testing, and all of that. So, but when you have them in the same program, a biomedical engineering program, the clinicians start understanding and appreciating the timelines, while the engineers start understanding the urgency and how to get this trade-off between effectiveness and safety on one hand and speed on the other hand. It's important to note that OE does not have a biomedical engineering program, so in this regard, OE is something of an outlier. But I think that has happened because we have all the other programs here domiciled in OEU, and they are quite mature in the university. So this has allowed OEU to work, the collaboration OEU to work, even though we don't have a biomedical engineering program. I expect this will be a rarity in LMICs. I expect that in LMICs you will need to have biomedical engineering programs to be able to sustain cross-disciplinary collaboration. Now, talking about innovation required for LMICs, if we are going to follow the path to developing our robots, we need to be able to innovate. And once again, this requires collaboration, but this time between academics and practitioners. So this requires locations that have not just the academic disciplines, but also teaching hospitals in close proximity. So this is an important requirement. If we are going to have innovation in rehab robotics in a country, you are going to have multiple locations that have colleges of health sciences, teaching hospitals, and faculties of engineering in close proximity. And one would say that the greater the number of clusters of these, the higher the chances that you can have sustainable robot-assisted therapy expertise in the country. Talking about manufacturing, LMICs will need to be able to do something about their manufacturing capacity if they are to tool the path of developing robot-assisted therapy technologies. This is not an area of strength for most LMICs, and things are not going to change overnight. And it's important to note that we can't wait for industry to take the lead on this, because industry is profit driven and there's really no market yet for RATs or even any of the high-tech alternative therapies. There's no market yet. And we think an important way to get things started here is that researchers must bootstrap things by taking advantage of the fact that international funding agencies are happy to fund LMIC research in medicine and agriculture. And so researchers interested in RATs must work towards research grants with significant capacity development and components. So we'll quickly take a look at some of our research projects in the IFE Rehab Robotics Research Group. So the point here is to review how problem selection can lead to emergence of a research agenda or research agenda targeting LMICs. So the first of these is the platform for upper limb stroke rehabilitation, which is depicted graphically here. So this platform, this robot, has 5 links, four which are shown here, and at the end of this link you have an end effector that has a sensor that can measure how much force is being applied by someone who grabs it. So the point of this is to allow a user, a stroke survivor, to move this end effector following an already predefined trajectory, and to quantify the deviation in the actual movements carried out by the user versus the required movement. So the idea here is that the robot has motors that can actuate the link, so that even in the absence of any effort by the user, the robots themselves, the motors themselves, could actually make the link move in such a way as to cover the trajectory, the prescribed trajectory. So at the end of the day, if we can find a way for the robot to quantify the error in the movement of the user, what is then required is for the motors to supplement the movement or the effort of the user, so that you have this cooperation between the motor and the user. So the motors generate just the torque required to offset the errors in the user's movement. The assumption is that a recovering stroke patient will have more errors, more deviations from the required or prescribed trajectories, which the motors will then correct for. And the assumption is also that over time, as the stroke patient improves, as the motor function is improved, the motors will not need to correct so much for the errors by the user. Now there are a number of other elements in the system as a way of helping to generate enough muscular force to move the end effector. We have functional electrical stimulation applied to the muscles of the hand. Okay, and then finally, I should re-emphasize the point that the robot and the user work cooperatively. So the robot detects the actual effort being applied by the user and then augments when necessary. But one might ask, what if you have a user is unable to actually muster enough force to be detected by the sensor embedded in the end effector? How then does the robot know what the user is trying to do? Imagine a user who is still incapable of generating any force, and we want them to use this robot, and the user is trying to move his hand forward, for example, and but is not generating enough force for the sensor to detect that force. Is it possible to have this robot still understanding or knowing the intention of the user in that scenario and working cooperatively with them? So that's why we're introducing brain-computer interfacing into this equation. It's been known for quite some time, over 10 years, that you can actually detect the intention of a user to move their hand or leg merely by capturing EEG signals from their scalp. And so what we are trying to do in this project is to use EEG to detect the intent of users to move their hand, even when they can't muster enough force to be detected by the sensors in the end effector. So hopefully, when the EEG tells us the user is trying to move his hand in a particular direction, then the robot can actually use this information to supply the force required to move the end effector, even when the user's applied force is not enough to be detected by the end effector. I should quickly mention why this is an important problem to look into. You see, it's well understood. The belief now is that very early, when you begin rehabilitation very early after stroke, very quickly after stroke, it improves outcomes. But the problem is that for many patients, for many stroke survivors, if you begin too early after stroke, they might not be able to generate enough force to be detected by the sensors. So we are working towards a system that you can use with patients very early after stroke, even when they can't generate the required muscular force to be detected by the end effectors. In controlling the system, we use something called impedance control for the robot hand interface, which reduces the risk of injury to the patient and we use iterative learning control for reducing errors across multiple iterations. So this means that as a user moves through multiple iterations of tracing the required trajectories, the robot becomes gradually better at correcting for the errors in the user's movement, because we use something called iterative learning control. This is a picture of the robot during our initial usability tests, which unfortunately some of the coupling parts failed, and we are working on replacing those so we can actually complete the usability test and finalize the study protocols, because we intend to complete this and deploy it clinically to quantify its effect, if any, on the outcome of stroke rehabilitation. The study will require us to compare patients who use this robot to patients who use only conventional therapy. And I should mention quickly a constraint imposed by a choice of architecture, because we are using what is called a planar robot, which means the robot can only move forward, backwards, left, right. That means it can move only on one plane. It can't move, for example, up, down, which introduces some serious constraints in what kind of exercises patients can carry out when they're using the robot. So our study will be designed in such a way to ensure that patients who use the Pulsar robots also benefit from exercises that work out all their muscles, so they are not disadvantaged by using this robot. And you would ask, why do we use a design constraint to a single plane then, if it might have these disadvantages? And the answer is that this is just, remember, this project is also a capacity development project where we're trying to develop in-house this expertise, and already we have an updated design we're working on that is much more flexible than Pulsar, and we expect that over the next few years we're going to roll out much more complicated, much more sophisticated designs than Pulsar. And it's important also to mention the other goal of this project is to begin to tease out, to reveal problems that will be of particular interest or importance to LMICs. And that, I think, is one of the things targeted by the next project, which we'd like to look at, which we are working on, and that's the Pulsar Sim project. So it turns out that when you build robots to be used by patients for rehabilitation, that there's a process where you have to let each user use the robot for 30 minutes or thereabouts to carry out something called system identification, which basically means you take measurements, you understand the anatomy or the dimensions of the user's hands or body, then you factor that in, and you use that to modify some parameters in the control of the system to make the robot much more effective. This usually takes time, and so we got thinking, if our goal, if we're interested in minimizing the effort required to develop robots for LMICs, in which every small logistical problem takes on an added complexity, then it might be a good idea to eliminate as much of the difficult steps as possible. And so we thought, is it possible to replace the user in that system identification process by having models of users, essentially replacing the user by a simulation of a user? And so that's what the Pulsar Sim project is. It's a simulation-driven project. It's a simulation-driven system that we hope to use to develop the control strategies for rehab robotics. And as mentioned here, the control strategy is actually very, very important. Of course, there are a number of different control strategies. We have high-level control, we have low-level control strategies, and the way these impact the robot is actually depicted in the diagram here. So for your robot, the architecture of the robot is largely defined or determined by the high-level control strategy you want to take. So for example, we are using what is called assistive high-level control. there's something called challenge-based high-level control approach, and there are other types of control strategies. And so the high-level control strategy determines the robots, the general details about the robots, but then your low-level control strategy determines the control algorithm you use to control the elements in the robot. So for this, you have things like position control, adaptive control, and impedance, admittance, and so on. I think I did mention earlier on that we're using impedance control for Pulsar. So in determining which of these to use and in testing whichever you have decided to use, usually you use a human subject for the system identification. The point of the Pulsar Sim project is to replace that human subject with a simulated human. And this is made more difficult by the fact that there are actually very few, if any, accurate human controller models, because of, human beings are highly non-linear, and it's difficult to get accurate models of humans. And so, as I said, usually we use real humans in the loop, which is a time-consuming process. And in this project, we want to explore the possibility of using a human model instead of a real human. This is made easier by the fact that we now have systems with relatively accurate biomechanical models of the human anatomy, the human systems. We have, for example, a software called OpenSim. There's one called Anybody. And what these do is allow you to write models that show how human musculoskeletal system behaves in response to all kinds of stimuli, including external forces, including activation signals along the nerves, activation signals to the muscles. You can actually describe the muscle structure, the muscle behaviors. You can do all of this in very close detail and then simulate how the entire body responds to these various stimuli. So our hope is that we take a software model of a human developed in OpenSim, and we try to replace all these elements which a real user will normally provide in a user-robot interaction. We replace all of this with the simulated model, and then try to see if we can use this to develop control laws that actually work. And what does work mean? Work means that, as I told you about Pulsar, the robot is supposed to reduce the error in the trajectory over time. So if the control model is working, then over time it will reduce the errors in the trajectory of a user using the robot. So in other words, we want to see if we can do this using simulated humans. And to do this, we developed 6 pathological models and 1 normal model. The pathological models represent 3 different models of weakness, 2 of synergy, I believe, and then 1 of spasticity. And this depicts the software environment where you can see the OpenSim component has the human biomechanical model, which allows us to, we can run kinematic and kinetic routines on that human model. What this basically means is we can tell if the human arm is at this location at this point in time, and the robot is applying a force of X Newton, how does the human arm change its location? If the human arm was moving with a velocity of this in 3D space at this point in time, and the robot is exerting from the motors a force of this at this angle, how does that change the angle of this human arm? So when we have this information from the OpenSim side, we can actually use this, send this to a MATLAB Simulink system that's simulating a robot. So the robot in MATLAB Simulink takes the information from OpenSim about how the human body musculoskeletal response is being changed by the application of forces by that same robot, and this allows the robot model in MATLAB Simulink to predict future states. In other words, the robot model requires information about how is the human musculoskeletal model affected by my current states, which includes position and forces and torques. And knowing that, the robot model is then able to predict the next state of the robot. Our hope is that combining these 2 components allows us to model accurately the interplay between a human arm in this case and a robot, and in the bargain we actually can then change the control models. In effect, this allows us to test different control models using a robot defined in MATLAB Simulink and a human defined in OpenSim. So this of course means that we can define multiple versions or multiple models of humans in the future and change the control laws and test different human anatomies, different dimensions, and different control laws, which of course is the point of the whole project. And here we've shown two plots. On the left we have something that was generated from a simulation showing how the normal subject, so what we have here is this: the dark ellipse here shows it shows the required movement, required trajectory, right? So think about the pulsar robot now. In fact, this was actually generated with the pulsar robot, so maybe I should start with this on the right. So here you have this trajectory required for a user to follow, and then we had a user run through 10 different iterations of trying to move the end effector of pulsar to follow this exact trajectory, and the traces in red were generated from the 10 different movements. Okay, so we did something similar using the pulsar sim. Now in pulsar sim, using the normal model, we asked the normal model to generate 10 trajectories to follow the predicted trajectory, and you can see some slight similarities in how the errors are introduced into the movement of the model when you compare it with the errors of a real human. And here we show the root mean square error generated from the trajectories of 6 simulated users in one of the modes. I won't talk much. The pulsar sim operates in 2 modes. The free moving load mode is one in which the user just moves the robot without the robot actually cooperating or helping the user. So what we have here then is these are 7 models in pulsar sim. We ran the simulation asking the system to show how the trajectories for each of those models would what the trajectories would look like, and then we calculated the error, the mean root square error between the actual trajectories and the black trace, which is the required trajectory. And what we found is that the RMSE error for the unimpaired model was less than 3 millimeters, while for the 6 pathological models you had these respective errors. So what we then did is that in running this, we then ran this in a mode where the TC mode, where the robot is actually assisting the user. This is also simulated, and you can see the difference that the RMSE errors for the unassisted operation of the human model was, the ICA is 6, while the errors are much lower when this was run in an assisted mode. So what this effectively means is that the simulated humans in our model, when we ran the trajectories, they had relatively high errors depending on the different pathologies being modeled, or different impairments being modeled. But then when we simulated the system using the robot to assist them, the errors reduced, which shows in a sense that the robot was able to help them reduce the errors in their movement. And one final thing we did on this, we wanted to see if the geometry of the robot affects the performance of the pulsar sim system. So we modified the geometry of the robots as defined in the system here, and then we ran the simulation again, and what we found is that the errors they are comparable. The errors haven't really changed much between the 2 different geometries. So this is actually the assisted mode, not free moving load. This is the assisted mode. Sorry about that. So in other words, the simulation is not really affected the by changing the architecture or the dimensions of the robot. But it's important to mention here that there's a major caveat, which is why we consider this pulsar sim to be a work in progress. And that caveat is that the models have not yet been validated with real human data. So what that means is that if you got a real human with pathologies or with impairments to try to track these trajectories, and the errors follow a particular pattern, can we prove unequivocally that the errors generated by our models for a particular impairment are the same as the errors you will find in a human subject? Or bluntly, are we sure our models behave exactly the way a human would behave? In order to do that, we need proper validation studies. And the difficulty here is that we found out that motion capture of human subjects can be expensive. The cheapest motion capture system we found was a few hundreds of thousands of naira, and prices go up to tens of millions. And so right now we've opened up a new research problem into using pose estimation. It's a very interesting machine learning problem which you can look up, using pose estimation as a basis for cheap motion capture. And we're making quite some progress here. And this again is another pointer to the fact that when LMICs work on RATs, will reveal problems that will be of interest to us to explore, because most HICs will not have problems with getting motion capture systems, but it's a problem of LMICs, and this has led us to opening a new frontier in pose estimation. So this is work in progress, very much work in progress. Finally, I'd like to quickly talk about another project we are working on. And I talked about the use of brain-computer interfacing in detecting the intent of the user to move their hand, or in a case where the user is so weak, the motion is so impaired that you can't detect the way they're trying to move their hand. I talked about using BCI. So actually BCI, there are many different approaches to BCI, but what has become clear over the last few years is that you have improved outcomes in rehabilitation when you start the process very early. And a point I should quickly mention here is that if you don't have a human supervisor and you have your patient interact with a machine too early after stroke, then you're increasing the risk of injury, which is of course why, as I said, we are trying to find out ways to understand what the user wants to do, even when he can't actually muster the force. So in doing this, if you noticed on the pulsar diagram, we're using EMG, electromyography, to detect the movement of muscles. But sometimes the muscles don't move enough for you to detect the forces, okay, after stroke. And so brain-computer interfacing, as I mentioned, is something that we're exploring, that has been also been explored by others before now. And when you're doing brain-computer interfacing, the point is to try to read, really, you are reading what the signals from the brain, from the cortex directly, usually, to determine intent or determine something about the state of the brain itself. And there are many modalities that you can use for this. There is MEG, there's PET, and there's FNIR, which have all been used as ways of effectively reading signals from the brain and then determining from that what the user is doing or thinking. And of all these modalities, EEG is superior for a number of reasons. And EEG, there are actually three classes of EEG. We're using scalp EEG, which is what you normally see in movies, where you have electrodes attached to the scalp of the subjects and you can read electrical signals from the electrodes. There's also intracortical EEG, which actually requires you to open the cranium and then insert the electrodes into the brain itself. And there's ECOG, electrocorticography also. So, but surface EEGs, scalp EEGs are cheap, they're compact, they have high temporal resolution, which means you can actually rapidly, quickly, the changes in the activity on the scalp or activity on the cortex, you can actually monitor those changes very rapidly compared to other modalities. And scalp EEG is also very safe. Unfortunately, it has low spatial resolution. It means that if you shift the electrode of the EEG by a few millimeters on the scalp, you are not likely to see a change in what you are reading, because the EEG. So in a sense, the reading the EEG signals from the scalp is like standing behind a wall and listening to 5 or more people talking. Those are like your sources, and then trying to determine the location of each of those 5 people from behind the wall. You can do this, but you're gonna have low spatial resolution. So the wall in this case is like the cranium, and the EEG is like the EEG electrode is like you listening behind the wall. So in other words, your EEG has low spatial resolution, but it's advantage that we found I mean researchers in the area will find ways to work around. Okay, so now when you do brain computer interfacing, classically what people have done is to read the signals from the brain, in this case read the signals from the EEG on the scalp, and then using what you read from the scalp to determine one of a discrete number of outcomes. So for example, it's very well known that when the user moves, when someone moves their hand, there's a well-known effect where the amplitude of the signals measured on the scalp on the contralateral side, that's the other side of the body, there's a slight drop before that movement. I'll take that again. So before you move your hand, if you intend to move your hand, your right hand for example, a few instants before you actually move your right hand, an EEG with an electrode on the left side of your brain over the motor cortex, you can actually see a drop in the amplitudes from that electrode. This is actually a very well-known result, which is called event-related synchronization / event-related desynchronization. So these classical techniques, in other words, allow you to do one, so you can detect, do you want to move his hand or is he not moving his hand? That's a binary outcome. Move hand, not move hand. Move leg, not move leg. Classically, you can do this very easily using BCI techniques. But recently, a new approach has emerged where you actually try to more accurately determine the movement. So you want to actually measure what's the velocity of movement, what's the direction of movement, what's the acceleration of movement. This is called continuous decoding, and it's much more difficult. So there have been results that have been announced recently on continuous decoding, and some progress has been made. But we wanted to see if it's possible to use a low-cost bioamplifier, such as the OpenBCI, to decode those kinematic variables. This hasn't been done before, because once again, high-income countries, cost is usually not a constraint, so they have high quality. Most researchers in this area have high quality bioamplifiers, but we wanted to know if you have something like the OpenBCI, can you still carry out continuous decoding. So here we provide some details about the setup, and this shows our custom built electrodes cap using dry electrodes. The point here, of course, was to try to keep cost as low as possible, because remember, low cost. So we use 3 subjects, right-handed, and so on and so on. None of them had any previous experience with BCIs. And then we use something called filter bank common spatial pattern algorithm, which we use to filter out the different frequency components from the EEG we acquired from the scalp of the subjects. We look for frequencies in 4 Hz bands between 4 and 40 Hz. And in synchronizing data from multiple sources, we use something called lab streaming layer, and we use OpenSesame for designing the interface or presenting cues to the subject. So more details about the data acquisition. This is how the rate at which we acquired the EEG data were filtered, and these are the 11 electrodes from which we acquired the signals. For each subject, we had 2 sessions where we had 10 runs per session, and each session, and we had per run, we had 10 trials. So for each trial, what this means is that for each trial, we just said we have a 9-second cue, where 9-second period where we give an arrow that tells the user to point in a particular direction, and then there's a beep, and then the arrow shows where the user should point to, which they don't actually do, and then when the beep comes up, they actually do the pointing, and then this cue shows them when they return their hand, and then you have a blank, which means they just wait for the next trial. And we use linear regression to learn the relationship between the EEG signals, the features in the EEG signals, and the kinematic data, which we acquired using Microsoft Kinect sensor. We had Microsoft Kinect sensors, which were also capturing photographic data from the user, and so we compared the actual data captured by the Kinect sensor, Kinect camera, to the data acquired from the scalp, from the EEG, and then we used a linear regression model to map, to learn the relationship between them. So results for the 3 subjects, this shows how well we're able to predict, or how well our data detected whether the user was actually responding to that cue with their right hand or with their left hand. So here what this means is that for actual right hand, we actually detected that right hand was raised from just the EEG, and once the data was misclassified as left hand being raised. And for the actual left hand, all 18 actual left hands for user A were detected. For user B, when user B actually moved his right hand, the system classified 17 of 23 as correctly as the right hand being moved, but 6 of them were wrongly classified as left hand being moved. While for user B also, when user B moved his left hand, 20 of the 24 movements were correctly classified as left hand being moved, while 4 were wrongly classified. So you have similar results for user C. This shows the coefficients of the regression we ran between the actual data acquired, features acquired from the EEG, and the movements as detected by the Kinect sensors. And this compares the results to results from previous studies. And it's important to note 0.2, 0.4, 0.3, these are not very high coefficients at first glance, but if you look, you'll find out that there are much more expensive systems that have been used for continuous decoding. Continuous decoding is hard, it's a new area, so there are much more expensive systems that have been used that actually had even worse results than we had, or comparable results than we had. And while you do have some better results, okay, but by electrode costs are still much higher than we had. In fact, we had the lowest reported by electrode cost for any EEG system that has been used to do continuous decoding. This is the lowest you will find in literature right now. And what this tells us is that yes, we can use open BCI, cheap bioamplifiers like open BCI, for continuous decoding. And much more importantly, it means that cheap amplifiers can be used as basis for BCI for robot-assisted therapies. Because remember, continuous decoding was the more complicated as type of BCI. If we're using discrete BCIs, then clearly open BCI will be even better. And so that's about that study. So here we are saying previous studies, the average by electrode cost was $243, with the cheapest being $105, and we achieved $59, so on and so on. So this leads to some confidence that BCI components for robot-assisted therapies can use low-cost bioamplifiers. Of course, this is something that still requires some work. But it's important to remember the point of all those studies we went through. And the point is to show, is not to show, we haven't set the world on fire. We don't have any big results yet, because we've been working in this problem space for just 2 years. But the key is to show that when research groups in LMICs work in problem space of robot-assisted therapies, we can start identifying problems that are of more particular interest to LMICs. So when we start getting more research groups working in this problem space, we'll start exploring new problems, or more problems that will be important in helping to domesticate technologies required to successfully mount robot-assisted therapies in LMICs. And usually the key is low cost. The key word we look for is low costs because of the constraints LMICs have. But it's important to stress that it's not just about low cost, it's about getting the perfect trade-off between low cost and acceptable performance. So we hope we'll see more research groups in LMICs getting into this problem space. And one final thing is I believe the British Medical Research Council recently shared the result of a study that showed that going from research results to clinical adoption, widespread adoption clinically can take 17 years. That means when you have a therapy shown to be effective in the lab, it might take up to 17 years for it to become widely adopted. It takes quite some time. So this means that LMICs need to get into this game fast, because going from showing expertise to actually getting this adopted will still take some years. So I think the final message then is that we don't just need to get into RATs, but we need to get into that problem space as soon as possible. Thank you for your time. I'd like to thank Dr. Michelle Johnson of the GRASP Laboratory, University of Pennsylvania. We've been working with the group for a year now, and we're making fantastic progress. They have a very keen interest in getting this technology to work in LMICs. OpenBCI and NVIDIA have graciously donated made hardware grants that have enabled us to do the work reported in this webinar. And the Pulsar project is being funded by the Tertiary Education Trust Fund, and for this we are very grateful. Thank you very much once again for your time.